Question number 31. When a system is taken from, let me draw the graph that they have in the book. So the graph looks like from A to C, then from C to B, or A to D, and then D to B. And then there is a path from B back to A, going like this. So I have 4 states, A, B, C, D, and I have 5 processes, from A to C, C to B, or A to D, D to B, and then B back to A. So that's a graph. The question says, when a system is taken from A to B along ACB, along the ACB, 90 joules of heat flows into the system, and yet the work done is 60 joules, is done by the system. So when they say 90 joules of heat goes into the system, which means Q is positive, so this is 90 joule, Q is positive, is equal to, well, internal energy, change internal energy, plus the work done. But the work done by the system to the environment is 60 joules. So the work done is 60 joules. So obviously, then the change in internal energy, in this case, will be 30. Okay, 90 minus 60 will be 30. So we now know that the change from A to B is 30 joules. In other words, B will have higher internal energy by 30 joules compared to A. So question number A is, how much heat flows into the system along ADB if the work done by the system is 15 joules? Now, from ADB, which is from here to here to here, if the work done is 15 joules by the system, so how much heat will be flowing into the system? So Q equals to what? So if it is from ADB, that process, from here to here to here, you have to remember is that when they say work done is 15, they're really saying that this area here is 15. But earlier they said that the work done from ACB is 60. So the whole thing underneath this whole thing will be 60. So in other words, we have this being 60, but then this portion is 15. So this is 15, the whole thing is 60, so this must be 45, this area. Okay, anyways, so they say how much is the heat, but the heat is delta U plus 15. But delta U in this case is the same delta U from A to B, because A to B does not depend, the change in internal energy does not depend on the path. But work does, heat does, but not the internal energy. So that means this is actually the same A to B. Doesn't matter if you travel from A to C to B or A to D to B. The internal energy is independent of the path. So we could use the same internal energy, 30 joules, and plus 15 joules of work, so it will be 45 joules of work, and since this is positive, then the heat will be from the environment to the system. So the question is, part A is, how much heat flows into the system along the path ADB? So the answer then is 45 joules. And then part B says, when the system is returned from B to A along the curved path, the absolute value of the work done by the system is 35. The system absorb or liberate heat. So in other words, when they say is that this is 45, they just didn't tell you if it's positive or negative. That is the work done from B to A following the curved path. The work done is, 35, not 45, 35. They said that this is 35. They didn't say it's positive, negative. But since it's from right to left, the area is always going to be negative. So this will be negative. So therefore, the W should be negative 35 joules. If W is negative, then that means that the work is not done by the system to the environment, but rather it is from the environment done to the system, because this is negative. So part B says, when the system returned from B to A along the curved path, the absolute value of the work done by the system is 35. Does the system absorb or liberate heat? So if that is the heat that they're talking about, then we have to look at Q. Now Q is delta U plus, in this case, negative 35. But delta U we said was 30, right? So 30, but that would be from A to B, but now we're going from B to A, so this will be a loss of 30, and then minus 35, so it will be a loss of 65. So heat will be, in this case, negative, but Q stands for the amount of heat the environment supplies to the system. But since this is negative, that means the system is liberating 65 joules to the environment. So this means the system releases or liberates 65 joules to the environment. Now, next one, it says, does this, okay, so how much heat? So this is the amount of heat, 65 joules. And part C, if U of A is 0 and U of D is 8, if U of A is 0 and U of D is 8 joules, internal, okay, energy, find the heat absorbed in the process AD and DB. From AD, which is from here to here, what is the heat absorbed? Well, during the process of A to D, you can say QAD is delta U plus the work done. But we said that this is 15 already, so that's going to be 15 from left to right. So that's positive 15. U, they said, is from 0 to 8, so that will be 8 plus 15, 23 joules. So heat is positive, which means the environment is pumping in 23 joules into the system. That's positive. And then now we want another one. What is the heat absorbed in the process of dB, from D to B? From D to B is from here to here. So internal energy, well, we know that from here to here was 30 from the past, or this one is higher than that by 30. So if this is 8, then difference here will have to be 22. The difference in energy. So this will be 22 plus the work done. Well, there can be no work done if it is isochoric. So P delta V, there's no delta V, so this is 0. So the heat energy pumping in should be just 22 joules from the environment to the system. So those are the answers. Okay. And then we do number 33. Number 33 says you have a diagram that looks like this. You have A, B, C, D as 4 states. So you have A, B, C, D, 4 states. And that you can have, again, from A to B, B to C, or A to D, D to C, okay, in that order. So what they're saying is these are 4 states of a system. The volume of the system for at A and B, which means this one is VA, and at C and D is just called VC, okay? The pressure for AD, A and D, this one is called PA. And then PC for B and C. So this is called PC. Alright, so basically you have the coordinates of all 4 corners. Now, the internal energy of the states are just given the letters of each one. So this is going to be UA, UB, UC at this corner, and UD at their individual corners of their own internal energy. Okay, so now for each of the processes from A to B, and B to C, and A to D, and D to C, you want to find the work done by the system during the process, the heat flowed during the process. So we want to know the work done and then the heat flow. Okay, so let's do it one at a time. From the state of A to B, from the process from A to B, Q is delta U plus P delta V. But there is no work done from A to B because it's vertical isochoric, and therefore there is no work. The change will simply be UB minus UA, and the work done is 0 from A to B. So heat from A to B is simply UB minus UA. Okay, so that one is easy. And then from B to C, for the process B to C, Q dC is change of internal energy plus work done, P delta V. Change of energy will therefore be UC minus UB, then plus constant pressure, so that would be PC, times the difference in volume, which is VC minus VA. And of course, this is the work done, WBC. Okay, WBC will just be this part, but QBC will be the whole thing. And then we have from A to D. So AD, for the process AD, QAD is very similar to the previous one. All you have to do is change internal energy, that will be UD minus UA, and then plus the work done, which will be PA times the change of volume, PA times VC minus VA, and this part is WAD, the work done from A to D. And for the process D to C, the heat from D to C is a change of internal energy of UC minus UD, but there's no work done. So, or you can say the work done from D to C is 0. Okay, so here are the works. So that is part C. That is part B. Part A and part B. Part A says find the work done by the system during the process. The work done by the system during the process will be these four. And part B says what's the heat flow into the system during the process. Heat flow into the system will be the whole thing here, whole thing here, whole thing here, and whole thing here. And then part C says the system can be taken from A to C along either the path ABC or ADC. So you want to go from A to C, you can go this way or you can go this way. Find the net heat flow into the system and the net work done by the system for each path. So in other words, I want to know if I go for the process ABC, well naturally in that case I have to add these two. Okay, so Q AB plus Q BC, add these two up. So the work or the total energy will be, well, you can see that the UB will be cancelled if you add these two up. It will just be UC minus UA, as UB will cancel, and then add these two, but this is 0, so it's simply plus PC VC minus VA. Okay, and then if you did ADC, that is going from here to here, then you will add these two up, that is QAD plus QDC, which if you add these two, you will cancel out to minus UD. So all you have is UC minus UA, and then plus these two added together, which is PA times VC minus VA. Now obviously, if you compare the two, the internal energy change is the same because internal energy does not depend on the path. That proves that here is just UC minus UA. However, the work done is different. The work done from VC minus VA is the same. However, when you multiply by PC, this is the whole area. If you were to go from A, B, C, much more work done will have to be done by the system. And but if you were to go from here to here, then the work done will be much less, only this amount. So the question is, find the net flow, heat flow into the system, and the net work done by the system for each path. For the net heat flow will be this for each system. This is net heat flow, and the net work done, the net work done for ABC will be PC, VC minus VA, and the net work done for ADC will be PA times VC minus VA. So, they say, for which path is net heat flow greater? Well, obviously, the greater the work that you add to the change means the greater the heat flow. So, therefore, from ABC, path ABC, the heat flow will be greater. ABC, then if it was from ADC, the heat flow will be much greater if you go through ADC than if you go through ADC. Alright, now what else do they ask? So, which path is the network greater? Well, ABC is greater. And then they say, part D, a friend tells you that the amount of heat flow should be the same for both the path ABC and the path ADC, since the initial state A and the final state of the system are the same for both paths. Well, how would you respond? Well, the internal heat may be the same, but the work done is not the same. But since the amount of heat is the internal heat change plus the work done, therefore, even though the internal increase in the internal heat is the same, but because the two different paths take two different work done, so ABC having a higher work done require higher input heat than ADC, which is less work done, therefore require less heat input. So that's how you will respond. So that's how you answer question number 33. So, and the answer BC is BC VAC, yep. And then WAD is PA BC minus VA, that's correct. VDC is correct. So QAB, which is this one, is UB minus UA only, yes. And QBC is QC minus QB plus PC VC minus, that's correct. I'm just checking the answer right now, and this is correct. And then QDC is UC minus UD, no, that's 0, that's correct. And then QAB, which is QBC here, is UC minus UA plus PC VC minus VA, that's correct. And ADC should be UC minus, the work ABC is just PC VD minus VA, or C and D are the same anyways. And that is a greater work. And they didn't write down the lesser work, which is ADC is the lesser work, but ABC is a greater work. Okay, so that's 33. Let's do 35. So 35 says, in a certain process, 2.5 times 10 to the 5 joules. In a certain process, this amount of heat is liberated by a system. If it's liberated by a system, this will be negative. So Q is negative. Is liberated by a system, and at the same time, the system contracts under a constant external pressure. So pressure is 9.5 times 10 to the 5th Pascal. Constant pressure, so isobaric. The internal energy of the system is the same at the beginning and the end of the process. Well, if the internal energy is the same, then we are talking adiabatic. So that means delta U is the same. Sorry, I don't mean adiabatic. If internal energy is the same, then the heat is just the work done. Heat is just the work done. Most likely this is isothermal. So let's see. The internal energy is the same at the beginning of the process. Find the change in volume of the system. It is not an ideal gas. So find the change in volume in the system. They want to know what is the change in volume of the system. It's not an ideal gas, they said. Well, we know that the first law of thermodynamics means change in heat is change in U plus work done. So they said that this is negative 2.5 times 10 to the 5th. That is the heat released. Yet delta U is 0. So the work done, which must be P delta V because it's constant pressure. So the change in volume would just be this divided by P. So negative 2.15 times 10 to the 5th divided by pressure, which is 9.5 times 10 to the 5th. So 2.15 divided by 9.5. So then negative 0.226. Negative 226 cubic meter. So, and they only ask for what is the change in volume in the system. Well, that's it. So the change in volume in the system would just be negative 0.226 cubic meters. So it simply means that the final volume is smaller than the initial volume. And that's it. And that is the right answer too. Number 27. Oh, 37. Number 37. A thermodynamic process in a liquid. A chemical engineer is studying the properties of liquid methanol. She uses a steel cylinder with a cross-sectional area. Okay, we'll better write it down. Cross-sectional area A being 0.02 meters square. Cross-sectional area is a steel cylinder with that and containing this amount of methanol. So the volume that it contains is 1.2 times 10 to the negative 2 cubic meter of methanol. The cylinder is equipped with a tightly fitting piston that supports a load of. Okay, so there is a load on top of this piston. There is a piston on top of the cylinder. Okay, some sort of a piston on top of the cylinder, and it has a load, which means a force of 3.00 times 10 to the 4th Newton, which means really a pressure, right? Because force on top of A will be the pressure, so you can actually figure out what the pressure is being applied, and that will be 1.5 times 10 to the 6 Pascal. So, really what they're telling you is just the pressure. The temperature of the system is increased from 20 degrees to 50 degrees. So, 20 degrees to 50 degrees. And for methanol, the coefficient of volume expansion. For methanol, the coefficient of volume expansion is 1 times 20 times 10 to the negative 3 per degree Kelvin. So, coefficient of volume expansion, which is like this, is proportional to delta T, and this alpha, well, we should call it gamma now. This gamma is for volume, or you can call it beta. Beta is 1.20 times 10 to the negative 3 per degree Kelvin, That is the coefficient of volume expansion. And the density, rho, for methanol is 791 kilogram per cubic meter. And the specific heat capacity at constant pressure, okay, so they give you Cp, is 2.51 times 10 to the 2.51 times 10 to the third joules per degree Kelvin per kilogram Kelvin. All right, so that's Cp. Neglect the expansion of the steel cylinder. Find A, the increase in volume of methanol. How much volume has increased of the methanol? I guess due to the change in temperature. Okay. Well, they already gave you the coefficient of expansion, so we need to know from the coefficient of expansion exactly what the delta T is, multiplied by the constant one point time, and then multiplied by the initial volume, which is this, will get you the change in volume. So delta V over V is the beta times delta T. Now delta T is just 50 minus 20, which is 30. So change in volume then can simply be beta times 30 times initial volume V. Then we'll find out what the change of the volume is. So change of volume, according to this calculation, will be beta, which is 1.2 times 10 to the negative 3 here, per degree Kelvin, but it's 30 degree Kelvin times 30. And then multiplied by the current volume. The current volume is 1.2 to the power of 2 negative. So the amount of change is 4.32 times 10 to the negative 4. Okay, so that is the change in volume. So first question is, find the increase in volume of the methanol. So this is the increase in volume of methanol. Okay, 4.32 times 10 to the negative 4 cubic meter, and that's correct. And part B, it says the methanol work done, the mechanical work done by the methanol against the 10 times 10 times 3 times 10 to the 4th Newton force. What really it is saying is that now that you have moved this much, but this much is against the pressure being supplied, and we know that work done is pressure times change in volume, and this is the change in volume, and the pressure we will figure out was this much. So 1.5 times 10 to the 6 Pascal times the 4.32 times 10 to the negative 4 cubic meter, then we'll get the work, the amount of joules, and that will be 648 joules, and that is correct. Okay, and then next one, part C, says the amount of heat added to the methanol. What is the amount of heat added to the methanol? Well, the heat added to the methanol, okay, Q is delta U plus P delta V, right? So the change in under constant pressure, we said was basically NCP delta V, the NCP delta T. So all we need to know is how many moles are there, and multiply by Cp, which we were given, times the change in temperature. The number of moles, well, we have to therefore figure out how much volume we're dealing with to begin with, okay, and therefore figure out what the density, from the density to figure out how much mass, and divided by the molar mass of methanol, then we can figure out how many moles. But originally we have a volume of this, and the density is that, so mass is equal to volume times the density, and the volume was 1.2 times 10 to the negative 2, and the density is 7.91 kilogram, so that means times 3 grams per cubic meter. So let me figure out what the number of grams we're talking about. 1.2 to the 2 negative times 7.91. So I'm now talking about 94.9 grams. Now I need to know how many, what is the molar mass of methanol. Now methanol is, the formula for the methanol is CH3OH. CH3OH. So the molar mass is 12 plus 4 plus 16 is 16 plus 16, 32 grams per mole. So I now divide that by 32 grams per mole. I now have N as 2.966 moles. Therefore, I can now plug in here now 2.966 N times Cp, which is given to us 2.5 times 10 to the 3, and change in temperature we know is 30 Kelvin. So I just need to now multiply 2.513 times 30. So I get a change in heat, which is 2.23. Here, gotta be careful. This is in kilogram Kelvin. This is in kilogram Kelvin, which means that I cannot use moles. Okay? So they gave us this in kilogram Kelvin. So I have to use kilogram, not moles. So I actually didn't need to do any of these. I just need to change this number into kilogram. So that is 94.9 times 10 to the negative 3 kilogram, because the unit here is in kilogram. So 2.51 times 10 to the 3, then times 30. Okay, so let's see if that will give us the answer. Times 2.51 to the 3 times 30. $791. Oh, this is not 7.91, so it's 791. So, okay, here's another mistake. So I say 1.2 2 to the negative 1 times 791 cube. Okay, this is actually let me see, 1.2 to the 2 to the negative times 791 kilo. So this is actually 9.49 kilogram. Okay, so if I just use 791 kilo times 1.2 to the negative 2 is 9.49 kilo. So this is just 9.49 kilo times 30 times 2.51 cube. I get 7.15 to the 5th. Okay, so and that is correct. 7.15 to the 5th. So basically, here the unit they gave us was kilogram. Okay, not grams. So you got to be careful here. So, and also the density here is in kilogram as well. So if I had used everything in kilogram rather than convert to gram, because I really did not need to figure out a number of moles, because the Cp given to us was in kilogram, not moles. So I just need to multiply by the kilogram. Okay, so the heat added is just the NCP delta T, but this doesn't need to be moles, it's just be the mass. Okay, so anyways, we got the heat, and heat is now correct. And then let's see, that's part C, and then part D is the change in internal energy of the methanol. What's the change in internal energy? Energy of the methanol. So this is the amount of work done, and this is the amount of heat added to the system because it's a positive. But then the amount of work done is only this. So the change in internal energy is this minus that. So if you want to calculate that, it should be 7.15 to the 5th minus 648. So if you did it that way, knowing the Q is 7.15 times 10 to the 5th joules, and that equals to change in internal energy plus the work done of 648, then change in internal energy will be just Q minus 648, and then the answer is 7.14 times 10 to the 5th joules. But that is very much similar to what we had in heat, 7.15. So the amount of work of expanding against the pressure is 648 is negligible, really. So the amount of change in internal energy is 7.14 times 10 to the 5th. So based on the result, explain whether there is any substantial difference between the specific heat capacity, Cp, and Cv for the methanol under these circumstances. Okay, so, well, I think that's the thing, is that this internal change, delta U, which is supposed to be NCV delta T, is 1.4 times 10 to the negative positive 5 joules. That is what it's supposed to be, by subtracting the work done from the heat, and the change in the internal energy is NCV. But now if you divide this one to get CV, you get 7.14 times 10 to the 5th divided by change of temperature of 30 and divided by mass of 9.49 kilogram. I get a CV of 2.509 times 10 to the 3rd kilogram joule per kilogram Kelvin. Now if you compare that to this one, it's practically the same. If you round it into 1, it's basically CP and CV are the same. So in this case, CP and CV are actually, that means gamma is almost 1, because it's not quite an ideal gas. So in this case, based on your results, explain whether there is substantial difference between the specific heat capacity, CP, at constant pressure, and CV at constant volume for methanol under these circumstances. So no substantial difference.